And this here is our fourth and final lecture regarding aortic regurgitation. Our learning objectives with this particular lecture is to understand the principles for calculating regurgitant fractions, explore the basis for calculating regurgitant orifice areas, and also apply the Pisa principle as a way to estimate aortic regurgitation. Regurgitant fraction is simply an expression of the percentage of regurgitant volume compared to the normal forward stroke volume. It's represented as the formula here. So regurgitant fraction is equal to the regurgitant volume times 100, because we're working with percentages, divided by the stroke volume of a confident valve. Regurgitant orifice areas can also be calculated. Much in the same way that we determine the area of a stenotic valve, we can assess for the size of a leaking area. We have already described that the flow is equal to the cross-section area multiplied by the velocity time integral. So substituting what you know to evaluate, regurgitant volume can be also expressed as Q, and effective orifice area equivalent to cross-sectional area. So we end up with the formula here, and then we want to know the effective orifice area. A slight rearrangement of our calculation is equal to regurgitant volume divided by the velocity time integral of the regurgitant volume. With our aortic valve, we have a regurgitant volume of 34 mils. An aortic valve has a stroke volume of 108 mils. So simply it's represented as 34 times 100 divided by 108, 31%. To work out the effective regurgitant orifice area, we need to also include the VTI, regurgitant volume, and that worked out to be 35.2 centimeters. So simply 34 divided by 35.2, our effective orifice area works out to be 1 centimeter squared. Then working along with our numbers to determine severity, working with regurgitant volumes and regurgitant fractions, working with these sort of ranges, we can quite easily establish whether someone is going to be mild, moderate to severe, or have severe severity. Note with the assumptions listed earlier for determining of stroke volumes, a regurgitant fraction compounds the problem further by introducing the leaking valve stroke volume twice. The proximal isovelocity surface area is another method we may employ to evaluate a regurgitant valve. It is also based on the same principle of conservation of mass. It is important to note that many students misinterpret isovelocity as isovolemic from previous physiology learning. This calculation makes the assumption that flow through a regurgitant orifice is equal to flow with a convergent hemisphere just above it or below it, depending on their axis. We're using specific velocity defined on the machine to determine the radius and thus our hemisphere. The velocity at this point is neither accelerating or decelerating. It is uniform or unchanged, thus the term isovelocity in the name. However, blood is accelerating as it moves closer towards the orifice. Therefore, at high velocity equates to a smaller radius. As blood progresses towards the regurgitant orifice, it increases in velocity and the hemispheres associated with each velocity progressively decrease in size. The specific velocity of any specified hemisphere is uniform. And here we have our formula. So flow through the regurgitant volume is equal to flow convergence. So the cross-sectional area of the regurgitant volume times the velocity is equal to the cross-sectional area of the hemisphere times its velocity, rearranging things across. And the fact that we're not really working for a cross-sectional area, we're actually looking for a hemisphere. So regurgitant orifice area is 2 pi r squared times the velocity that the aliasing is actually occurring, the point where we measure from the leaflets to the first line of aliasing, divided by the regurgitant velocity. So putting these into practice, the radius of a hemisphere can actually be difficult to measure under normal imaging conditions. So to ensure the best representation, the colour baseline is moved in the direction to flow through the valve, typically upwards. And so we have our set of values that we acquire. So regurgitant velocity 4.1. Now important to note that we're actually measuring the early diastolic to measure the peak there. The radius that we're actually measured from the leaflets to the first aliasing dome is 0.4 centimeters, and the velocity that the ascent occurred by looking at the color scale on the side of the screen was 0.45 meters per second. Throwing it into our calculation and then making sure we convert the centimeters, we get an effective orifice area of 0.11 centimeters squared or 11 millimeters squared. Regurgitant volumes can be calculated using the stroke volume formula that we know well now. Note here again we have moved back to velocity time integral. We're assessing all the velocities moving through the valve over a period of time rather than at an instantaneous point. The Pisa method is readily utilised for the estimation of regurgitant volume and severity. In the case of stroke volume calculation for mitral regurgitation, typically the RVOT is placed with the sample volume through a normal stroke volume, but this can't be used when there's pulmonary regurgitation. So Pisa does not have this limitation. We're not assessing a secondary valve that needs to actually be competent. Pisa is used as a guide for aortic regurgitation. There are significant challenges in measuring the hemispheres, given that the degenerative calcification is very common and the valve position is deep within the image where image quality is lower. As with the limitations seen with other stroke volume calculations, the radius is an important component, and error in determining of the value would lead to an inaccurate value of regurgitant areas. The radius is measured at a specific point in time, such as early diastolic filling for the mitral valve or early diastole for aortic regurgitation. An effective orifice estimate is made with flow at that point in time. This will over or underestimate the true anatomical orifice area. Beat-to-beat variation, as seen in previous calculations, can lead to error, thus it is important that numerous measurements are taken. Even in sinus rhythm, a sonographer who averages 3 to 5 measurements will deliver a much more desirable result than someone who does just one. In the presence of atrial fibrillation, bigeminy, or frequent ectopic beats, then up to 8 measurements will deliver improved accuracy. There are also considerations for determining of hemispheres. The isovelocity contours or effective shells flatten immediately proximal to the orifice, effectively changing the shape, and the assumed volume will therefore be incorrect. Use a baseline shift that is not too extreme, i.e. just a little bit higher, minimizes this effect. Additionally, the orifice shape may be irregular, so the hemisphere doesn't actually represent the flow of convergence. The aortic valve cuffs are semilinear in shape. They do not form a flat surface also when they come out. And thus, the hemisphere sitting on top of the aortic aspect will only approximate the actual volume within. Another issue arises where there could be significant flow rising from multiple points. However, we only measure one hemisphere. So in summary, a regurgitant fraction accompanies a regurgitant volume calculation to give further confidence in calling the severity of regurgitation. Care must be given, however, as further error can be introduced with the regurgitant fraction calculation. And the Pisa is a useful tool for assisting in determining aortic regurgitation severity. It has significant limitations and best approximates the actual value.